Hello, ladies and gentlemen, and welcome back. Root Beer here, looking at C2 on our 2012 open paper. We fill a 3x3 grid with O's and 1s, zeros and 1s. We score 1 point for each row, column, and diagonal whose sum is odd. Okay. For example, the grid on the left has 0 points, because this column's even, this column's even, this column's even. So no points for any of the columns. The rows are even because they have just 2 1s and 1 0. So no points there. And then that's an even diagonal. And then 1 plus 0 plus 1, even diagonal. So, okay, yep. I'm getting the 0 sum. And the grid on the right has 3 points. So this column has a sum of 3. This row has a sum of 3. 2, 2, 2, 2, 3. So there's 2 points. And then one diagonal is 2, and the other diagonal is 1. So, yes, 1, 2, 3 points, because 3 odd sums. Okay. So I understand their system now. Let's continue reading on. So, 2 marks. Fill in the following grid below so that it has exactly 1 point. No additional work is required. Many numbers are possible. Many answers are possible. You only need to provide 1. Okay, so we just want 1 point. We could play around with this, and indeed, let's. So, you know, I don't have a particular intuition behind the problem, so let's put a 1 right here. Let's make this column our 1 point. So let's put zeros everywhere else, and that would give me a sum of 1. Now, I don't want this row to have an even sum, so let's put a 1 here and a 0 here. Let's see if that works. Now, we don't want this column to be odd, so let's put a 1 here and a 0 here. And we'll put a 0 here. That keeps these sums, and this diagonal up here becomes 2. But if I put a 0, I have to put a 1 here, otherwise we don't get an even diagonal. But then this 1 would put a 1 here as well, and that would be 2 points. So, okay, it didn't quite work out, but we're just trying to learn. So maybe let's keep that 1 up in the top corner. Put a 1 here. 1 here. This 0 is doing fine. I'll put a 1 here. So now I've got 2, 2. I need to put a 1 here, and that would make it a 1. Otherwise, I'd get a 0, and I'd have a 1 here. So, maybe not put a 1 on the diagonal. Let's put a 1 off on the side. Zeros there, so we'll have this column be my 1 point, and then well, we should probably have at least another 1 over here. That's gonna force my diagonals to be unattended. So let's actually see. Maybe we can make this column a 3. And then put a 1 here, and a 1 here. And I need yet another 1. 2 marks. I'm agonizing a lot over it. Let's try a 1 here, and we'll make one of the diagonals. This is a 1, this is a 2. We could try 1s here and here for sums of 2 and 2 and 2. And then I think 0s everywhere else. And that does it. So it just has 1 point. Okay. So I like an introductory question like that. It basically says, do you understand what we're talking about? And, you know, can you just sort of work through a tiny simple case? Now, what have we got for B and C as well? Okay, so for B, determine all grids with exactly 8 points. So I need exactly 8 points. Now you get a point for each row or column or diagonal. Well, there's 3 columns, 3 rows, and the 2 diagonals. So in order, write this down, in order to get 8 points, we need a point for each row, column, and diagonal. Okay, so how are we going to do that? So we need each row, column, or diagonal to be odd. I think as we explore the theory for this question, maybe we should look at what our diagonals are. So maybe we call this A, B, C, D, E, F, G, H, I. And so the rows are A plus B plus C, D plus E plus F, G plus H plus I, and these need to be odd. Our columns are A plus D plus G, B plus E plus H, C plus F plus I, and our diagonals are A plus E plus I, and C plus E plus G. Alright, so we've got a lot of these, but there's certain numbers. So A, for example, appears in 3 sums. E appears in 4 sums. I'm trying to sort of approach this almost like filling in a magic square, and usually what you do with a magic square is you analyze rows and columns and things like that. But D only appears twice, for example. Now, if I add up all the rows, so these are all equal to odd, and if I add up 3 odds, I get another odd. So we can see, add up row-wise, A plus B plus C plus D plus E plus F plus G plus H plus I. You could also do it column-wise. There's going to be an odd plus an odd plus an odd is equal to odd. The entries are 0s and 1s, so we need an odd number of 1. So that's a nice important fact that we've got here. Now, can the diagonals teach us anything? Well, so let's say looking at diagonals, we've got A plus E plus I plus C plus E plus G is going to be 2 E's and then an A and an I and a C and a G, and this is equal to an odd plus an odd, which is necessarily even. Now if we can take 2E away from both sides, we notice that A plus I plus C plus G must be even. It's even minus an even, which is even. So corners have an even number of 1s. And so maybe we can sort of zone out certain regions that's okay. You know, the blue area has to have an even number of 1s, and doesn't necessarily matter what the center is, and that sort of a thing. But, where can we go from there? Can we get any other combinations? Well, I think similarly, if you take any row and column pair, the numbers where they don't intersect must contain an even number of ones. But I think that's going to be too much information that I can't effectively use it. So maybe we should just do cases. And I like the idea of the corners. So let's do a case with zeros. So 0, 1s. Let's say no ones in the corners. Okay, does this yield some interesting or obvious results? Well, in order to get the diagonals to be odd, you need E to be 1. Okay? But in order for this row and this row to be odd, you also need 1s. And for this column and this column, you also need 1s. And then we get 3 and 3 as well. So this is our only option. Okay? And you would probably just say, you have to fill it in. So step 1 would be E has to be 1. Explain that. Step 2, these rows and columns need to be odd. Therefore, we get these 1s. And then you wouldn't just say, well, we filled the whole thing in. Job well done. You would say, and then step 3, verify that the other rows and columns are also odd, which they are. Okay. So, another option, we could have 2 1s in the corners. And we actually have 2 options here. They could be option 1 in the same row, or they could be, well, no, we could have in the same column, or they could be in the same diagonal. We're going to have to deal with each case. Let's see whether or not these... So the row and column one sort of should be listed as just as one because they're going to be mirror images. But let's say we've got 1 and 1 here. Well, in order to... I'm gonna number these steps. So 1, in order for this row to be odd, we need a 1 here. Okay? And, we also know we've got zeros everywhere else. Well, step 2, I would say, in order for the diagonals to be odd, we need a 0 here. E has to be 0. The middle one has to be 0. Alright, well, step 3, in order for this column to be odd, we need a 0 here. And then, oops, we have all zeros. So step 4, can't be done. And similarly, no way to have 2 1s in the same column. How about if they were in the same diagonal? So we'd have 1 and 1. So here we go, step 1. Oh, we also have zeros in these other locations. So step 1, we have to have a 1 here, otherwise we wouldn't get these columns here to be odd. Step 2, I would say you would need zeros here in order for these rows and columns to be odd. And then we just have to double check. Step 3, this column and this row, these also add up to an odd number. So this works. So does the other option of having the opposite diagonals. Okay, so there's 2 more options right there. Okay, and what else could we have? So I suppose we could also have four 1s in the corners. So we get 1, 1, 1, 1. Step 1, You need to have a 1 here, otherwise you can't get the diagonals to add up to be odd. We do this... No, we did something. We did another cross for another other question. Step 2, I would say these rows and columns need 1s, otherwise they're not odd. And step 3, we just verify that, oh yeah, these also add up to odds. And there's no symmetry here, so for B part, we can either have 1s as a cross, or the 2 single diagonals, or 1s everywhere. So these are the only cases. There we go. And we haven't missed any. And the 2 in the same row and 2 in the same column definitely didn't work out. So, okay, good. Alright, so I'm liking the question so far. We've explained ourselves. Particularly, we've explained, well, really you didn't need any of this work looking at the rows or anything like that. But we did have to, looking at the diagonals was definitely something that needed to be written up. And saying that the corners have to have an even number of 1s, that was probably worth a mark. And then probably got some more marks based on the answers that we were able to come up with. Okay. So, C part, let E be the number of grids with an even number of points, and O be the number of grids with an odd number of points. Prove that E equals O. Well, you just swap them, don't you? I hope it's not as anticlimactic as I think it's going to be. But I think... So we'll show how to take a grid with an even sum. And turn it into... Maybe the marks are just for the wording of the argument. One with an odd sum. And vice versa. So why will this work? And the number of even sums must equal the number of odd, even sum grids must equal the number of odd sum grids, because they're what's called in a one-to-one correspondence or a bijection. You can't have one without also having a corresponding one of the other kind, so they can be paired up. And they can be paired off quite nicely. But consider A, B, C, D, E, F, G, H, I. If it has an even number of points, maybe this isn't as obvious as I'm thinking. We'll find out as I try and word my argument. So actually, let's say if it has P number of points. We'll talk about oddness and evenness later. Let's look at 1 minus A. So if A was a 0, there's now a 1 there. If A was a 1, it's now a 0. Okay. So we do this basically, you don't have to phrase it like this. You could just say swap all the zeros into 1s, all the 1s into zeros. The reason I'm doing it like this is I'm saying, let's compare rows. So you might call this grid G, and you might call this, I don't know, G prime or something like that. So the first rows, G and G prime, So the first row you'd have a plus b plus c. Well, now you have 1 minus a plus 1 minus b plus 1 minus c, also known as 3 minus a plus b plus c. So if this is odd, well, an odd minus another odd was going to be even. And then what other rows do we have? D, E, F. Well, that's going to turn into 3 minus. G, H, I on the bottom row for G. And what do we have now? 3 minus G plus H plus I. And we could write the rest of them out as well. I'll just do it very, very quickly. So in G prime. So what do we have? A plus D plus G, B plus E plus H, C plus F plus I, and then our diagonals A plus E plus I, and C plus E plus G. But with each one in G, you're just adding up those 3 things as well, but now they've got a minus sign in front of them, and you're also adding up the number 3. So you can complete this, or you could just say similarly and state the big conclusion, which is this. So observe G is equal to G prime prime, or G bar bar. Basically, the process undoes itself. So, and G bar has 8 minus P points. Here's why. Each odd row in G gives an even. Why even? Well, because it's 3 minus an odd. Well, we don't even have to say row. We can say each odd row, column, or diagonal gives an even row, column, or diagonal in the corresponding position in let's say G bar in corresponding position. So what else could we say there? Then I guess we could say so P equals number of odd rows. No, I don't want to keep saying rows, but oh wait, hold on. 8 minus P though, if O is odd, then G bar is also going to be odd. Oh, rats. So it is a little harder than I thought. Okay, good, because I wasn't giving them enough credit there. So it's not the case, because we've got 8 for our sum here. So let's flip the page and see if we can come up with a better way. So I still like this idea of correspondence, but is there a way for me to tweak it? Is there something we can do to fix it? So if we start with A, B, C, D, E, F again, G, H, I, is there a way to take an odd sum, an odd point grid, and turn it into an even point grid? That's the challenge, because otherwise, you know, if one of them had 3 points, 8 minus 3 is still 5, so it's still an odd number of points, so okay, a bit of a waste of time, but that's because I didn't think it through. I still might get marks for something for what I wrote, but we might try something else. Well, what can we do? So again, what are our rows and columns? If we add them all up, if we start with something that's odd, we should get some... no, that was if they were all odd. So, oh, if we... What if we add up all the rows and columns and all of that? So, a little similar to what I was saying earlier, that certain numbers appear more than once. So, let's add up the rows, add up the columns, and add up our two diagonals. So, A plus E plus I, C plus E plus G. And I got A, D, and G, B, E, and H, C, F, and I. So we're going to get 3 A's. And we'll get... Let's actually cross these off. So 3 A's. I'm seeing 2 B's. Yeah, because B is not on a diagonal. It's just in a row and a column. So similarly, we'll have 3 C's, 2 D's. We already said earlier 4 E's, 2 F's, 3 G's, 2 H's, and 3 I's. Okay. So if we add that up, that's going to be the same as... It's not going to be P, but it's going to have... We'll have same parity. Parity just means oddness and evenness as P. Because you'll have an odd number of rows, or odd number of odd-summed rows, columns, and diagonals. Okay, but things like 2B, 2D, 2F, 2H, these don't change parity. So once again, it seems like it's coming down to the corners. So we get the same parity as P there. So, could we maybe change the A's, C's, G's, and I's? Or would it be enough just to change A? So if once again I do something like call this G, and we make something like G bar, and we just change A. So put a 1 minus A there. Then shouldn't this work out? Then the points of G bar, say Q, have the same parity as 3, but now where our A slot was, it's a 1 minus A, 3G, or 3C, 3G, 3I. So this is 3 minus 3A plus 3C plus 3G plus 3I, which has the same parity. So parity, oddness or evenness, just as a reminder, it does not change if you add on an even number. So to get the plus A, what are we really doing? We're adding on 6A, but whatever A is, that's going to be even. So this has the same parity as this, and of course this section here has the same parity as P. So it has the same parity as 3 plus P. But since they differ by an odd number, well, not differ, but if P is odd, 3 plus P is even. So Q would be even. If P is even, 3 plus an even is an odd. Q would be odd. So they have opposite parity. And yeah, so this goes a little smoother. So notice that G is the same as G bar bar. And if, so it's the right idea, I sort of created the wrong function. Incidentally, a function that, if applied twice, goes back to the start is sometimes called an involution. Not something you need to know, just a little extra math fact. But notice that, and if G has odd number of points, then G bar has even number of points. So, just to summarize, we can pair up even point grid uniquely with odd point grids and so since each one can be taken and paired up, they can sort of be matched. The number of evens that you have has to match up with the number of odds. So E equals O, which is what they wanted us to show. All right, so stumbled a little bit there on C. I thought it was easier than it was, but I'd say I recovered fairly well. Yeah, there we go. So that's C2. So up next should be C3, and I will see you for that in the next video. Until then, take care.